Fall 2014 AP Calculus Prep Session, and this is part 2. This deals with problems relating f, f prime, and f double prime. And here we're going to deal with 6 problems that have short answers or multiple choice answers. Problem 1, find the interval or intervals where g of x equals 3x minus 2 over e to the power of 3x minus 2 is decreasing. So we're talking g, not g prime or g double prime. So this is a first level to find where the function is g is decreasing. We're going to take the first derivative and find where this first derivative is. If we find where the first derivative of this function is less than 0, we will know that over that interval where f or g prime of x is less than 0, there the function is decreasing. So we're going to find the first derivative of this, which we're going to call g prime of x. And what we have is the quotient of two functions. And so we're going to just kind of organize. So the high function is 3x minus 2. The derivative of the high, which we call d high, is the derivative of the high, which is 3. The low is going to be e to the power of 3x minus 2, and d low, or the derivative of the low, is going to be, using the chain rule and differentiating, we're going to take the derivative of this 3x minus 2 is 3 times e to the 3x minus 2. The function e to the x is very unique in the derivative of the function e to the x is e to the x, and so that kind of makes it easy. So we're going to go ahead and rewrite this. We're going to have low d high. So low is 3 times e to the, oops, not 3e, it's just going to be e. The low is e to the 3x minus 2 times d high, which is 3, minus high, and high is quantity 3x minus 2, and d low is 3 e to the 3x minus 2, and in the denominator, if we're going to take low squared, that's going to be e to the 2 times 3x minus 2. See, this is squared. We just multiply the exponent here by 2. And just trying to simplify, we look for a common factor between these two terms, and we see we have 3 e to the 3x minus 2 in both terms. So we can rewrite this as g prime of x equals 3 e to the 3x minus 2. That's our common factor between these two terms, times we have the whole, this is what we factored out, so we have left 1 minus, and then we factored out 3 to the e to the power of 3x minus 2. So what we have left is simply 3x minus 2. And we have all this over e to the 2 times quantity 3x minus 2. And basically simplifying this on the right, we have 1 minus 3x minus 2 is going to be equal to, I'm just going to do the rewrite here, g prime of x is equal to 3e to the 3x minus 2, and this is going to be, it's going to simplify to 1 minus negative 2 is going to be 3, and we have minus 3x over e to the 2 times quantity 3x minus 2. And so to find the critical numbers, we're going to set each of these as a numerator, each of these terms, or each of these factors equal to 0. So we're going to set 3e to the 3x minus 2 equal to 0. And we're going to set 3 minus 3x equal to 0. Well, in this, on the left, 3e to the power of 3x minus 2, there's no value of x that can ever make this left side of the equation equal to 0. So this can never equal 0 and is always, in fact, going to be positive. So, but this on the right, we can set this function equals 0 if we add 3x to both sides. We have 3 equals 3x, so x equals 1. That is our critical number. Let's draw our number line. And we have g prime above and g below. And our critical number is 1. And basically, we're examining this whole function here, but always 3 to the e to the power of 3x minus 2, that's always going to be positive. This denominator is always positive. The only thing in question is 3 is 23 minus 3x. And so we're just going to plug in a number less than 1 and see what happens. If we plug in, say, 0, well, we're going to have a positive value. So the function is going to be increasing from greater infinity to 1, but a number greater than 1, say 2, we're going to have 3 minus 3 times 2, we're going to have negative. So the answer to the problem is find the interval where g of x is decreasing on 1 comma infinity because g prime of x is less than 0. All right, so that will be our answer to number 1. Next, problem 2. Find the absolute maximum value of h of x equals 1/3 x cubed minus 4x on the interval -1 to 4 justify. Well, our candidates, we have candidates for this. We have to perform what we call a candidates test. And to do that, our candidates are always going to be our endpoints. And so we'll go ahead and make a table here. And we're going to have xy. We can put x, f of x. Or actually, we call this h of x, but that's okay, it doesn't matter. -1 is going to be a candidate, and 4 is going to be a candidate because they are the endpoints. Let's see here. As far as, let's go ahead and look at this h prime of x. Taking the first derivative is going to be 3 times 1/3 x squared minus 4. And so we're going to have h prime of x is equal to x squared minus 4. And so h prime of x factoring is going to be equal to quantity x minus 2 times quantity x plus 2. And we can set each of these equal to 0. So if we set x minus 2 equals 0, x plus 2 equals 0, we have x equals negative 2, and x, or actually that's going to be x equals positive 2, and x equals negative 2. So 2 and negative 2 will be our critical numbers, but negative 2 is to the left, is smaller than negative 1, so we're really not interested in this solution over here. We're interested in this one over here, where we have x equals 2. So constructing a number line, we put a number line of x equals 2, and we put h prime of x above and h of x below. We're going to just plug in here a value of less. We're going to plug into this function here a value of less than 2, say 0. If we plug in 0, we're going to have a negative times a negative, which is negative. So we're going down. And if we plug in greater than 2, let's say 3, we're going to have a 3 minus 2 is positive. 3 plus 2 is positive. So that's positive. And so what that means is that there is no other candidate, because we're trying to find the absolute maximum value, and this does not provide an absolute maximum. So we just need to evaluate the endpoints. And for that, we're going to say h of negative 1 is equal to 1/3 times negative 1 cubed minus 4 times negative 1. And so 1/3, negative 1 cubed is going to be negative 1 in thirds. That we're going to have negative 1/3, and that's going to be minus 4 times negative 1. So that's going to be plus 4. So that's going to be, let's see, 4, that's going to be negative 1/3 plus, how many thirds do we have in 4? Plus 12 thirds. So we're going to have 11 thirds right here. That's going to be a possible absolute maximum. Next, we're going to try this value 4. H of 4 is equal to 1/3 times 4 cubed minus 4 times 4. And so what that's going to give us is 4 cubed, that's 64, right? So that's going to be 64 thirds minus 16, 4 times 4, and 16, how many thirds are there in 16? I think it's going to be 48 thirds. And 64 minus 48 is 16 thirds. So we have 16 thirds, and this is going to be our absolute maximum. As far as justifying, in calculus, a candidate test will suffice. So usually a type of graphic organizer won't suffice as an argument. In this case, you can just label it. You can label candidate test. Okay, candidate test. You can do that, but I think you're okay. All right. Next problem, 3. A function f of x exists such that f double prime of x equals 20x minus 2 squared times x plus 1. How many points of inflection does f of x have? Well, we can just write out a number line analysis right like this. And we find our possible points of inflection by setting these equal 0. So our points of inflection are x minus 2 equals 0. So it's going to be x equals 2. That's a possible point of inflection. then set x plus 1 equals 0. So x equals -1. That's a possible point of inflection. So we're going to put f double prime here above and f below and set our possible points of inflection at -1 and 2. And at -1, we're going to examine this function and plug in values of less than -1. What's a value less than -1? Well, maybe -2. Well, -2 minus 2 squared, that's going to be positive. This is always going to be positive here, this point x minus 2 squared. But to the left, if we have -2, let's see, if that's -2, -2, that's going to be negative. So we're going to be concave down to the left of -1. And let's go to the right between -1 and 2. Let's try 0. We try 0. This to the left is still positive. We try 0 here. That's going to be positive. So we have positive. We have concave up. So we have one point of inflection already at x equals -1. Now we go to the right. Again, a number bigger than 2, maybe 3. Well, we plug in 3. This thing to the left is still positive, and 3 plus 1 is positive. So it's positive, positive. So we still have a concave up for greater than 2. So we only have one point of inflection. One point of inflection. And justification that it's not asking for is that because the function change f double prime of x changes from negative to positive at x equals 1, -1. Okay. Problem 4. An equation of line tangent to y equals x cubed plus 3x squared plus 2 at its point of inflection is, well, here we have, this is a level 1, the y equals, that's level 1, and point of inflection is a level 3 type of analysis. And so we need to go ahead and find the point of inflection. So to find the point of inflection, we need to first find y prime, and y prime is going to be 3x squared plus 6x, and that's going to be y prime. Y double prime is the second derivative, which is going to be 6x plus 6. Now, to find the point of inflection, we're going to need to set 6x plus 6 equal to 0. So 0 equals 6x plus 6. And so solving for x, we're going to have 0 equals 6 times quantity x plus 1. So x equals -1 is our possible point of inflection. It's really the only possibility we have. Again, to find the line of tangent, we need a point and a slope. Well, now we have an x value. We have point. It's going to be x equals -1, and y equals, we don't know. But we're going to plug in -1, so we're going to say y of -1 is equal to -1 cubed plus 3 times -1 squared plus 2. And -1 cubed is -1 plus 3 times -1 squared, that's going to be plus 3 plus 2, which is going to be equal -1 plus 3, that's going to be 4. So that's going to be our y value, 4. And next we need to find the slope. Well, the slope, which we're going to call m sub t, is going to be equal to the plugging in the first derivative. So I'm using this function up here. Y prime of -1, since that's our input value, is going to be 3 times -1 squared plus 6 times -1 plus 6 times negative 1. So we're going to have 3 minus 6 equals negative 3. And so our equation of a tangent line is going to be y minus y sub 1, which is going to be minus 4 equals our slope, which is negative 3. And we're going to have x minus x sub 1, which is going to be minus negative 1, x plus 1. And these are all these functions are in y equals. So just simplifying out, we're going to have y minus 4 equals negative 3x minus 3. And adding 4 to both sides of the equation, we're going to have y equals negative 3x, and that's going to be plus 1. So negative 3x plus 1, we hope it's here, and yes it is. Our answer is B. Next, let's go on to 5. The derivative function capital G is continuous and has exactly 2 zeros. Selected values of G prime are given in the table below. If the domain of G is the set of all real numbers, then G is decreasing on which of the following intervals? Again, we can try to work this out as a number line. I'm going to put right below the table. And we have exactly 2 zeros, and we look for where, let's see, the function has exactly, the derivative has exactly 2 zeros. So here's one of the zeros of the derivative at x equals negative 1 and at x equals 3. And so we're going to put G prime up above here and G below. And we're going to look at, to the left of negative 1, we have G prime as positive, so the function is increasing between negative 4 and negative 1. And between negative 1 and 3, we have negative values here, so the function is decreasing between negative 1 and 3. And to the right of 3, at least at 4 is the only one we can see, we have positive, so function increasing. And so the function is decreasing on which of the intervals? Well, between negative 1 and 3. And so here we are at x between negative 1 and 3. Our correct answer is C. Okay, on to problem 6. Let G be a function defined and continuous on the closed interval a to b if G has a local minimum at C where C is greater than A but less than B, which the following statements must be true. If G prime exists, then G prime of C must be equal to 0. Now we can just go ahead and make a little sketch of this. Let's see. We've got a function. There's a local minimum at C, and so the function is going to look, here we have, let's say we have A here, we have C, and we have B. Okay, so the function will be doing, we don't know what, but we know at C there's going to be a local minimum, and then the function can go down like this, or we don't know what the function is going to do other than have a local minimum at C. So for the function to be continuous, we're going to have a horizontal tangent line here at x equals C. So G prime of C is going to have to equal 0. So 1 is definitely going to be right. G of C is less than G of B. Well, here's an example that we have a relative minimum, but this is a kind of a counterexample because G of C is that it appears to be slightly greater. So relative minimum means it can just be at C and then continue going down. So 2 does not have to be true. G is increasing everywhere from A to B. Well, this cannot be. G of C is greater than G of B. we're going to be, to have a relative minimum, we have to have a function decreasing somewhere. So 3 cannot be right either. So A, 1 only is our correct answer. Anyway, that's our 6 problems on this part 2. I again hope this has been helpful to you. Thanks.